Okay, so last time we very briefly started talking about mathematics from India. And so today we're going to try to finish that. So let me first remind you of what we did last time very briefly, and then we'll continue from there. So we were talking about the mathematician Aryabhata, and he was a mathematician and astronomer. And we looked a little bit at the kind of mathematics that he did. But some interesting notes are what time period it was. So about 1500 years ago. He wrote a poem about astronomy and mathematics, and he wrote it in verse form. So a more poetic style of writing. And we're going to talk a little bit more today about using signs or half chords instead of chords. Okay, so let's talk about his sine function. So he actually had basically a table of sines. And so that's listed right here. So basically it's a table containing 24 values of the sine function. And these 24 values represent increments of, so basically this goes from basically 0 to 90 degrees divided into 24 even increments. And so that means that each increment represents 90 divided by 24, or 3.75 degrees, or if you write it in degrees and minutes, it's 3 degrees and 45 minutes. And although today, when we look at the sine as being represented in a circle, we think of it as having radius 1, and then the sine value is going to be, so if this is the angle, opposite over hypotenuse is opposite over 1. And so our sine is just going to be a number between 0 and 1. But for Aryabhata, his circle had radius 34, 38. And so his sine, so basically it's the y value in that triangle, is going to be between 0 and 34, 38. So for example, sine of 90 degrees, we would say it was 1, but he said it was 34, 38. So basically, if the angle is 90 degrees, the y value is the radius of the circle, which is 34, 38. So basically, these values here are, if the circle has this radius, then what's the corresponding y value? Now, why did he choose this number, 34, 38? Well, he did that so that his circle had a circumference of 21,600, which is 360 times 60. One nice thing about that number is that it has a lot of factors and makes it easy to work with. Now, this choice was actually due to an earlier Greek astronomer named Hipparchus. So as an example of trying to understand the data on this table, so we see that the third number is 671, and that corresponds to the angle 3 times. Remember this, the 90 degrees was divided into 3 equal parts of 3.75 degrees each. So the third value on the chart corresponds to the angle of 3 times 3.75, which is 11.25 degrees. Now, of course, we can check this value to see how accurate it is. Well, since our circle has radius 1 and his circle has radius 3,438, we need to multiply the sine of 11.25 degrees by 3,438, and we get, by plugging it into our calculator, 670.72 with some more decimals, and he got 671. So that's surprisingly accurate. So basically, if you take the correct value and round it to the nearest integer, that's exactly what you get. So very nice, very accurate result. Now, the use of signs was due to Indian mathematicians during this period. Before this, Greeks used chords instead of signs. So let's look to see how these two concepts are related. So think of a sine as a half chord of double the angle. So let's take a look at the picture. So basically you have an angle, any angle in a circle. So this is the center of the circle. And then the chord is just a line segment whose endpoints both meet the circle. And then the corresponding angle is, draw the angle through the center of the circle. And so if this is beta, this is the chord of beta. And of course, if you have a circle of radius more than 1, it would be a multiple. Okay, compare this to the sine. So if you take the sine, is going to be the vertical part of this right triangle. But if you double that angle, the vertical part gets doubled and the angle gets doubled. So the sine of alpha is half of the chord of double the angle. So this is the chord of double the angle. Half of the chord is going to be the sine. And then it turned out that half a chord was easier to compute with than the full chord. And then of course, when you're actually using this, it's all based on the idea of similar triangles. So you have different distances besides, what you see on the radius of the circle. And similar triangles will give you the results that you want. Now, what I'd like to do is look at a little bit of etymology. Etymology is the history of a word. So the word chord was used by that earlier Greek mathematician I mentioned, Hipparchus. So the actual word in ancient Greek is chorde, which meant gut, a string of a lyre, or a chord. And then what did the Indians call this? Jia, which meant a bowstring. And if you think about it, why would it be called a bowstring? Well, if you look at, for example, this image down here, this would be your bow, and then the string would be stretched tight. So it is kind of like a bowstring where the circle is the bow, and then the cord is the string, which is stretched tight so that it's straight. So that does make sense. But they didn't use the full cord, they used the half cord, which is gia ardas, which meant a half bowstring, but it was simplified to just ja or jiva. So that's the word that the Indians used for sign. This was later translated into Arabic as jiba. Now, here's the funny part of the story. In Arabic, you don't write all your vowels. And so in this word, there were no vowels written. There's only the J and the B. And some readers, when they were reading the mathematics, they didn't know, well, what is this word that they're using here? So some readers thought that it was jibe. So in other words, they filled in vowels that made sense to them. And what does this word mean? It means a pocket, a fold, a hollow, or a cavity. So then this word, jibe, meaning a cavity, was translated into Latin sinus, which meant cavity. But they translated the wrong word. And so this is where our modern word sign comes from. And basically it comes from a misinterpretation of an earlier Arabic word. So now what I'd like to talk about is another ancient Indian mathematician. His name was Brahmagupta. Of course, again, this is a period where Sanskrit was spoken. And so here's his name in Sanskrit. He was born in the year 598, and his main work was written in the year 628. So basically at the age of 30. And like Aryabhata, he was famous for both astronomy and math. So an awful lot of the astronomy, of the mathematics in India was partly to support their astronomy. So his father was also an astronomer. He worked in the city of Ujjain. So this is in basically north central India. He wrote his main work called Brahma Stuta Siddhanta in 628 at the age of 30. So let's see what are some of the ideas that Brahmagupta is responsible for. So he's known for cyclic quadrilaterals, and we're going to look at that a little bit more closely. Rules for zero. So rules for working with zero. So for example, what is zero? Remember that many earlier civilizations didn't even have the concept of zero, much less rules for zero. He also has rules for working with negative numbers. And even some things that today we would call number theory. So ideas that you might see, for example, in a number theory class. So there's the extended Euclidean algorithm, Pell's equation. We're going to look a little bit more at Pell's equation, and also rational triangles, which we're going to look at very briefly to see exactly what that is. Now, he used the value, the square root of 10 for pi. And when you calculate the square root of 10, what you get is about 3.16. So it's not really the most accurate value for pi that we've seen up until now in this course. So let's take a look at Brahmagupta's formula. And this is his formula for the so-called cyclic quadrilaterals. So the first question is, what is a cyclic quadrilateral? So basically what it is a quadrilateral inscribed in a circle. So what you need to have is that all four vertices of the quadrilateral are on the circle. Now, if your quadrilateral can be inscribed in a circle, then there's a formula for computing its area that Brahmagupta discovered. So first of all, let's let S is the semi-perimeter. So it's the perimeter divided in half So we're calling that the semi-perimeter. So S is A plus B plus C over 2. Then in that case, what is the area of this quadrilateral? So you take the square root of the semi-perimeter minus A times the semi-perimeter minus B times S minus C times S minus D, take the square root of the whole thing, and then that's going to be the area of a quadrilateral that's inscribed in a circle. Now note that this formula doesn't apply to just any old quadrilateral. It has to be one that can be inscribed in a circle. Now, notice that, let me just make a quick note. Any square can be inscribed in a circle, and any rectangle can be inscribed in a circle. So in both the case of a square or a rectangle, all you have to do is, and let me just draw a quick example. So let's say you have a rectangle. Draw the diagonals, and then what's the center of the circle? It's just the intersection of those two diagonals. And then what's the radius of the circle? It's just half of a diameter. So all rectangles can be inscribed in a circle, and therefore all rectangles are cyclic quadrilaterals. Now, the amusing thing about that is it gives us a way of checking to see whether this formula is right, at least for rectangles. So let's take a look. So in our example, all rectangles can be inscribed in a circle. And so in this case, instead of having 4 values, you have 2. So A and C are equal, B and D are equal. And then what is the semi-perimeter? Well, it's 2A plus 2B over 2, so it's just A plus B. So now let's go ahead and plug those values into our formula. So the area should be the square root of S minus A times S minus B times S minus C times S minus D. And remember that C is equal to A and D is equal to B. So S minus A is B, S minus B, so here's S minus B is A, S minus C, remember that C equals A, so S minus A is B, and then similarly S minus D is A. So we get the square root of A squared times B squared, and the square root of A squared times B squared is just A times B. So in the case of a rectangle, we get the correct formula that the area is just A times B. So it's just an amusing way to check to see that this formula actually does make sense. All right, I've just copied down the info again of the formula for the area of a cyclic quadrilateral. And now here's something interesting. Let's take the limit as D goes to 0. So imagine that this length is getting smaller and smaller, but you're still always working with a cyclic quadrilateral. So in that case, if this goes to 0, so imagine that this is merging with one of the other points. So if one side of a quadrilateral is 0, well, that means you really only have 3 sides. So it becomes a triangle. So then what's the semi-perimeter? It'll be A plus B plus C over 2. And then the area is going to be the square root of S minus A times S minus B times S minus C times S minus D, but D is 0. Well, this just gives you Heron's formula for the area of a triangle. So Heron was an earlier Greek mathematician. So the amusing thing about this is that it gives you a way to calculate the area of a triangle knowing only the lengths of the sides. So usually we think about, oh, how do you calculate the area of a triangle? Well, you think of one side as the base, you figure out what the height is, using trigonometry, and then you, calculate, the base times the height times a half. So here's an example. So let's say that you have this triangle where the sides are 7, 3, and 8. What's the area? Use Heron's formula. The semi-perimeter is 7 plus 3 plus 8 divided by 2, which is 18 over 2, which is 9. And so what's the area? It's 9 minus 7 times 9 minus 3 times 9 minus 8 times 9. Take the square root of the whole thing. So it's a square root of 2 times 6 times 1 times 9. Let's pull the 9 out because that's a perfect square. We'll pull that out as a 3. So we're left with 3 times the square root of 12. Now 12 is 4 times 3. 4 is a perfect square, so we'll pull that out as a 2. So we get 6 times the square root of 3. And so we get as the area of that triangle, 6 times the square root of 3. So here are some examples of rules for 0. And keep in mind that at this time in history, we still don't have algebraic notation. And so we have these rules, but they're written not in equations like we write them here, but they're written in words. So for example, he knew that if you added or subtracted 0 from any number, you get back the number that you started with. He knew that if you multiplied a number by 0, that you got 0. If you divided 0 by a number, you got 0. But here's something interesting. He didn't think of 0 as being an exception in the denominator. So he said that 0 divided by a number is 0, even when that denominator was 0. So his rule is 0 divided by 0 is 0. But this is something that not everybody accepted. And of course, today we don't accept that. Now, he also had rules for working with positive and negative numbers. So doing arithmetic on positive and negative numbers. So for example, he knew that positive times positive is positive, positive times negative is negative, negative times negative is positive. But also, of course, there's going to be rules for adding and subtracting positive and negative numbers. And we saw earlier that there were rules in China about adding and subtracting positive and negative numbers as well. So Brahmagupta actually had a definition for 0. So remember that 0 wasn't an entirely obvious concept at all. And so when we say 0, what do we mean? So he defined 0 as a number minus itself. So that seems like a pretty nice definition. So let's look at the etymology of the word 0. Now, in Sanskrit, which was Brahmagupta's language, the word was shunya. And shunya meant 0. And it comes from the word that means empty. Now, the Arabic word for empty is safra or sifra. And so the word sifra was used for the word 0 and also for the symbol used for the number 0. Then in Latin, Zephyrum was used by Fibonacci. So the Italian mathematician Fibonacci used the word Zephyrum in the year 1202. But then the Italians simplified this to zerum, or later 0. And so that's where we get our word for 0. It comes from the Sanskrit via Arabic to Latin and then later to us. Now, by the way, this Arabic word sifra sounds a lot like the word cipher. So actually, the word cipher comes from this as well. So a variant is sifra, which meant a numeral or zero. And then that became cipher, perhaps referring to letters converted to numerals. So the bottom line is that from this, we get both zero and cipher, and sometimes our word cipher does mean zero. So now let's take a look at Pell's equation. So this is something that is studied in number theory. So Brahmagupta studied this equation, which is considered to be very hard to solve in integers, as well as norm identities. So in other words, you take this equation, if you're just looking for any solution at all, that's not hard to do. You can plug in any value at all for X and then solve for Y, for example, and then you get a solution. You get a pair X and Y that solves this equation. But that's not good enough. We want our solutions to be integers. So just like when we found Pythagorean triples, we were only interested in integers that satisfied a squared plus b squared equals c squared. So this is like that. And then it turns out that this is actually a pretty hard problem in actually finding integers that satisfy this equation. So n is going to be some integer, and then you want integers x and y. So here's a quote by Brahmagupta. He said that if you can solve this equation in a year, then you are a true mathematician. So that's just a reflection of how hard Brahmagupta himself thought this problem was. Now, the solution that he came up with is x is 1151 and y is 120. And Brahmagupta solved this equation using clever methods. Now, by the way, this is something that was continued to be studied by mathematicians in later times. For example, Fermat rediscovered this equation in the 1600s. Euler, so Fermat was a later French mathematician. Euler was a later Swiss mathematician. He called it Pell's equation in the 1700s. This is named after John Pell, who wrote about it in the 1600s. So the next thing that I want to look at is rational triangles. So what is a rational triangle? Well, first of all, the sides of the triangle are rational numbers. So A, B, and C must be rational numbers. But furthermore, we want the area to be a rational number. Remember that when we saw Heron's equation for finding the area of a triangle, it involved taking the square root. And so as long as the thing that you're taking the square root of is a perfect square, you're going to get a rational triangle. So the next Indian mathematician that I'd like to look at is Bhaskara II. Here's his name written in Sanskrit. This was in the years 1114 to 1185. He was also known as Bhaskaracharya, which means Bhaskara the teacher. So like the other Indian mathematicians that we've seen so far, he was a mathematician and astronomer. His father was also an astronomer, and he was even the head of an observatory in Ujjain, which was famous for its temples. Now, Bhaskara was the last major mathematician in northern India for a while. He wrote 6 works that covered all known mathematics of the time. So let's look at an example of something that you would see in Bhaskara's works. So in one book, he gave the rule, the sine of A plus B is the sine of A cosine B plus cosine of A sine B. Of course, he would have written it in, a different form than we do, but it's basically just the angle addition formula for sine that we know today. So here's an amusing story in his work called Lilavati. So Lilavati was the name of Bhaskara's daughter. And notice that here it's the Bhaskaracharya, Bhaskara the teacher. So he cast her horoscope and discovered that the auspicious time for her wedding would be a particular hour on a particular day. So he placed a cup with a small hole at the bottom of a vessel filled with water and arranged so that the cup would sink at the beginning of the time that would be most auspicious for her wedding. When everything was ready and the cup was placed in the vessel, his daughter suddenly, out of curiosity, bent over the vessel, and a pearl from her dress fell into the cup and blocked the hole in the cup. And then the lucky hour passed without the cup sinking. And so Bhaskara believed that the way to console his dejected daughter, who would now never get married because her lucky time had passed, was to write for her a manual of mathematics. And so over here, this picture is pages from the manuscript of the Lilavati. So in general, it was believed that astronomy and astrology was a valid way of predicting the future. So let's look at an example of something that Bhaskara did in number theory. Well, he's famous for giving the first method of solving Pell's equation. So here's an example. Here's an equation, x squared minus 621 y squared is equal to 1. And then check out his solution. Let's see. I'm going to add commas just to make it easier to read these numbers. Okay, so the solution to this equation, x squared minus 61 y squared equals 1, is x is 1,766,319,049, and y is 266,153,980. Now, if you think about it, this is really crazy because he did this without calculators. And it turns out that this is actually the smallest solution to this equation. So that's interesting. Much later, in 1768, Lagrange, a later French mathematician, proved that this algorithm that Bhaskara came up with would actually terminate. So remember I said that Bhaskara was the last famous mathematician of northern India for a while. And that's because after this time period, the center of mathematics in India moved south to Kerala. And so this was known as the Kerala School, and it was founded by Madhava. So he lived 1350 to 1425. So what did he do? He wrote math and astronomy texts. He wrote a poem about pi. So it's amusing that that many of these ancient Indian mathematicians wrote their works in a more poetic language. And so basically, his poem about pi, in effect, gives us this value for pi. And if you compare that to the correct value of pi, you have to go, so these digits here are all correct. And then finally, the error only starts way down here. So it's a surprisingly accurate calculation of pi, and it was the most accurate at that time. So let's see what else he did. Well, he had some amazing results about infinite series, as well as infinite continued fractions. That's something that you also might see in a number theory course. I won't explain that here, but it's also a pretty cool concept. Some of these results about infinite series were rediscovered a few hundred years later by Gregory and Newton, Newton being the famous co-inventor of calculus. So around the year 1400, Madhava, and then around the year 1671, Gregory showed the following result: that the inverse tangent of x is given by this infinite series. Also, Madhava and then later Newton showed that the sine function is given by this series and the cosine function is given by this series. So series that we study when we take calculus. Now, of course, these are written in a modernized form, but the form that was given by Madhava so many years ago was equivalent to these modern versions of the series. So just looking at a couple of examples. So the inverse tangent of x is given by this formula. Let's just go ahead and plug in x is equal to 1. So if the tangent is 1, what should the angle be? Well, it turns out that pi over 4, which is tangent of pi over 4 is 1, is actually equal to the series that was given by Madhava. Now, this series converges very slowly, but it does indeed converge to the desired result, which is pi over 4. Also, the tangent of pi over 6 is 1 over the square root of 3. And so when you do the inverse tangent, pi over 6, plugging it into the formula, you get the desired result. And so this value actually converges very quickly, which is nice, because if I can calculate pi over 6 very easily with great accuracy because it converges quickly, all I have to do is take the result and multiply by 6 to find an accurate value for pi. And so this is how Madhava was able to come up with a very accurate value of pi. It's because of this formula. So this method of Madhava of finding pi is the first new method since Archimedes' method of using n-gons. Because remember that in China also, the method of using 96 gons was used to find pi. So this is now something brand new. Now, another thing that we should note is that India was the original source of the numerals that we use today. Now, if you look very early, like here is from 150 BCE, here's what the numbers look like. And then the earlier numbers were even simpler, more primitive, kind of reminiscent of the Chinese rod numerals. But in 850, if you look at these numbers right here, they do look kind of similar to the numbers that we use today, and they are indeed the source of the numbers. Okay, so that's all I have for India. And so what I wanted to do is at least get started a little bit talking about medieval mathematics. And so that's going to bring us to some Arabic mathematics, as well as some very early European mathematics in the post-Greek time period. Okay, so we're going to begin with just a very brief review of what is going on in the history of the world during this time period. So remember that in 212 BCE. That's when Archimedes died. And remember, Rome captured Syracuse at that time. And the Roman Empire continued to grow. And in fact, at some point, it became so big that it was split into the western and eastern halves of the Roman Empire. So Rome is over here, and that's part of the Western Roman Empire. And basically over here is the Latin-speaking part of the Roman Empire. Meanwhile, the East is Greek-speaking. So the Eastern capital was Constantinople. Here's Alexandria. And so this is all part of the Eastern Roman Empire. In the year 323, the empire became officially a Christian empire. And then a little later, in 395, the two halves had different emperors. In the west, the capital was Rome, again, Latin speaking. And in the east, the capital was Constantinople, Greek speaking. Then in the year 476, that was the fall of the Western Roman Empire to the Germanic tribes. However, Latin continued to be the official religious and scholarly language of Europe. And of course, Latin also evolved into the Romance languages. So that includes Italian, Spanish, French, Portuguese, and Romanian. Now, the official religion was Christianity, but in the West, it was Roman Catholic, and in the East, it was Eastern Orthodox. So basically two different branches of Christianity. Now, what language did the mathematicians use? Well, they mostly wrote in Greek. And the reason why is that Alexandria was the center of mathematics. So, for example, that includes Aristarchus, who wrote about astronomy and a heliocentric view of the universe, of the sun is at the center. Apollonius wrote on conics, 200 BCE. So this is all during the Hellenistic period. But later, you have the Roman period. So Heron, who I mentioned earlier, had a formula for calculating the area of triangles. So this is that same Heron that I mentioned. There was Ptolemy, who wrote on astronomy. There was Diophantus, who wrote about basically number theory. So the word Diophantine equations comes from the name Diophantus. Those are the equations, like we saw earlier today, where you're looking for solutions that are integers. And then Hypatia, who I mentioned, I believe, last week, who wrote commentaries. That was around the year 400. So the earlier were during the Hellenistic period, so where it was the Greeks who were basically in charge, and later was during the Roman period when the Romans were in charge. So as I mentioned earlier, the Western Roman Empire and much of the East fell to the Germanic tribes, the so-called barbarians, that was their word for it, as well as Persians and others. So the Roman Empire was stretched thin, and they suffered attacks. Now, the Eastern Empire became the Byzantine Empire. Then later, after the year 622, this is when the Islamic religion started to spread. And it was united under the caliphates. And then here, the dominant language became Arabic, and the language Aramaic declined. So the year 622 is considered year 1 of the Islamic calendar. So there are phases to the spread of Islam. So in phase 1, it was spread under Muhammad. Phase 2, spread under the Rashidun Caliphate. And then phase 3, under the Umayyad Caliphate. And so notice that this included much of North Africa, of the Middle East, and then as well as Spain. Now, during this period, at first, mathematics declined. However, in the 1800s, the Islamic world became very passionate about mathematics, astronomy, and science in general. And so this is actually very important to the history of mathematics, because around the same time period in Western Europe, this was the so-called Dark Ages. And so during this period in Western Europe, the study of science declined. And so while it's becoming important in the Islamic world, it's becoming less important in Western Europe. And so basically, it was during this time period that mathematics and science in general continued to grow. So the work in the Islamic world with math and science started with translations of Greek and Sanskrit works of astronomy and math. So these were translated into Arabic. Another interesting thing is the 9 symbols from India were adopted. So numerals. There were also innovations in algebra, geometry, and trigonometry. We're going to talk more about those. And then later, this work from the Islamic world later reawakened the interest in math and science. And so the Latin-speaking world basically learned a lot from what was going on there. So here are a few other interesting developments. So in the year 751 was the Battle of Talas, and some say that Chinese prisoners disclosed the secret of paper. So paper became the dominant writing material of the Islamic world. Then Baghdad was founded in the year 762 not far from the ruins of Babylon, and it became the capital. Then in the year 800, the House of Wisdom was founded. And so this was founded by Harun al-Rashid and his son Mamun, collected Arabic translations of Greek and Sanskrit classics. Now, Mamun sponsored al-Khwarizmi, who we're going to hear more about. And Ptolemy, the astronomer, was translated into Arabic as the Almagest. So al meaning the, and megiste means greatest. So that's why we have the word Almagest for Ptolemy's works. So let's begin talking about al-Khwarizmi. So usually we just refer to him as al-Khwarizmi. So he lived from about 780 to 850. Here's his name, Khwarizmi, written in the Arabic script. So Khwarizm was then part of Persia. It now is in Uzbekistan. And he worked at the House of Wisdom in Baghdad. Here I just have a little breakdown of what his name means. So his name is Muhammad. Ibn means son of. Musa, so he's the son of Musa. And then al, and Khwarizmi means a person from Khwarizm. So Muhammad, son of Musa, from Khwarizm. But he's still known as al-Khwarizmi to us, modern people. Okay, so here is his most famous work. Hisab al-Jabra wal Muqabala. And notice al-Jabra. Our word algebra comes from the title of this book. So let's see what the title actually means. Well, the Jabra part means completion or restoration, whereas the Muqabala means balancing. So basically it's restoration and balancing. So it really is algebra in most of the sense that we mean it. Now, of course, he's not using algebraic symbols, but he is doing algebraic operations. He's solving algebraic equations. So this is the first really complete account of quadratic equations and he uses geometric justifications. So he doesn't use symbols, but he uses words instead. The unknown, so the x that we would think of the x in the equation, was called the root or the thing. And it included some practical problems such as inheritance, lawsuits, trade, canals, areas, and volumes. So similar to some of the works that we've seen from earlier civilizations. Also, if you take a look at this image, this is what it looks like. There's a lot of words. And then there are illustrations using squares. So what he did was he used algebra, meaning completion or restoration. So think of completing a square, for example, and mukabala, balancing. So when we think about solving algebraic equations, we might think of adding or subtracting something from both sides. In order to reduce equations to standard forms. So let's look at an example. So here's an equation, x squared minus 7 is equal to 2 becomes x squared equals 9 by algebra, completing. So we're completing the square. The square is missing a 7. So we complete it by adding the 7 that's missing to get the x squared equals 9. Or 2x squared plus x is equal to x squared plus 1 becomes x squared plus x equals 1 by mukbala, balancing. So then what he does is he reduces equations to the following standard forms. The first one is bx equals ax squared. Then bx is equal to c. Ax squared is equal to c. So notice that this has an x and an x squared only. This has an x and a constant only. This has a square and a constant only. Next, you might have all three in one equation. But if you're thinking in terms of only positive numbers, then here are the forms that you would get. You could have the square and the number, or the square and the x with positive coefficients on the left and then a positive number on the right. Or the square could be by itself and then the x and the constant are on the other side with positive coefficients. Or the x could be by itself and the square and the constant are on the left-hand side. Now, there's one that's missing, and that is ax squared plus bx plus c is equal to 0, which today we find that to be just fine because we can solve that using negative numbers. So I think this will be the last thing we cover today, but let's just look at an example of actually solving one of these equations according to how Al-Khwarizmi would have done it. So 1 mol, which is a square, and 10 roots, remember a root is the x, equals 39. So in modern notation, we would say 1 square plus 10 roots is equal to 39. So x squared plus 10x is 39. So step 1 is take this number and divide it in half. So if you look at our picture, this is a square. Here is our x squared. We have the half of the 10, so we had 10 x's, so here's a 5x and here's a 5x. Now square that 5 to get 25. And so we get that x plus 5 squared. So that has to be the 25 that we added on plus our 39 to get 64. So x plus 5 is 8, and therefore x is 3. Of course, we don't consider this negative solution. And basically, he explains why this method works because he is completing the square. So if you go back and just take a look at this image, so everything shaded in yellow, that is our x squared plus 5x plus 5x. So that's our x squared plus 10x. All of that adds up to 39. So the yellow adds up to 39. In order to complete the square, we notice that this is 5 and this is 5. So this square must be a 5 by 5 square. So in order to get a complete square, we have to add on the 25, and we already had 39 here. So that's where this comes from. And so now this whole square is x plus 5 squared. So x plus 5 squared is 64, and therefore x plus 5 is 8. And then you get your x is equal to 3. So this is how Al-Khwarizmi solved quadratic equations. And it was using actual squares and building the squares and then figuring out what the answer would be based on actually completing a square. Okay, so that's all we're going to do for today. So are there any questions? Okay, so I'll go ahead and stop the recording.